Next, we're going to talk about the different properties of these vector arithmetic operations. Now, these properties, as we go through them, they should seem pretty similar because these are the same properties for the most part that we expect when we're adding and multiplying real numbers together. But remember, these aren't real numbers that we're dealing with. We are dealing with vectors. And so it's not a foregone conclusion that in this new space, with these new operations of vector addition and vector subtraction and scalar multiplication, that the same properties hold. That's why we call this a theorem. A theorem is a result that we have to prove. Okay? So we're going to discuss these, and then when we're done, I will prove a couple of these results. And then in your exercises, you will prove a couple of them as well. Okay? So we have three vectors, u, v, and w. These are vectors in Rn. N could be any number of dimensions. Okay? These properties will hold no matter if we're dealing with R2 or R7 or R306. Okay? And we have two scalars, k and p. So the first property we have is the commutative property of addition. We already discussed this one a little bit in a previous video. This means that if we add two vectors, u plus v, any two vectors, that's the same as adding v plus u. U and v commute. You could swap their places and get the same result. We have the associative property of addition. This means if you have u plus v plus w, it doesn't matter if you add u plus v first or if you add v plus w first. There exists an additive identity. We're going to call this vector the zero vector. And the additive identity here, it's just like the additive identity for numbers. If I take, any number, say 2, and if I add the number 0, well, hey, I just get 2 back. I get the same thing back. Okay? We're saying that there is a vector so that happens with all the other vectors also. Take any vector u, add it to this additive identity, you will get u back. And similarly, there exists an additive inverse. For any vector u, there exists some vector, which we're going to call negative u. So if we add those two vectors together, we get the zero vector. We have the distributive property over vector addition. So if we take some scalar multiple k, and multiply by the sum of vectors u plus v, we could distribute that k, and it's equal to ku plus kv. Distributive property of scalar multiplication, over scalar addition. Okay, we need another property because here we're adding the vectors, but over here, what if we add the two scalars together? Well, it turns out that distributivity also holds. Again, these are familiar properties. They should feel natural. But again, we're not dealing with numbers here, so it's not a foregone conclusion that these properties would hold. It turns out they do. Okay, and that's one of the reasons we're defining scalar multiplication and vector addition the way we have, so that these familiar properties hold. We have the associative property for scalar multiplication. Okay, so if we have two scalar multiples, k and p, and we're multiplying a vector u, it doesn't matter if we multiply the first scalar times vector u and then the second scalar, or if we multiply both the scalars first, then we multiply vector u. We get the same result. And finally, multiplication by 1. If we scalar multiply any vector by 1, we just get the same vector back. Okay? Well, as I've repeatedly said, these properties, they are true, but they are not a foregone conclusion. We can't assume them. We have to prove that they are true. This is going to be an important part of this class. We are going to introduce the idea of proving mathematical concepts. Proof is the foundation of all higher level mathematics. It's not enough just to do some calculations. You want to prove general results. So we're going to prove property D and also property E. Okay? So let's start with property D. And when you start a proof, it's usually a good idea to write the word proof. That way everyone knows, hey, this is what we're doing. We are proving a result. Now the problem has told us, the theorem itself has told us a couple properties. It has told us that U and V and W are vectors in Rn, and K and P are scalars, real numbered scalars. Okay. Now, when you prove results, make sure you are proving the general results. Example is not proof. It's not enough to do an example, because just because it holds in one particular case doesn't mean it always holds. That's what we are trying to do here. We are trying to show that these results always holds for every single case we can consider. We cannot, in this situation, test every possible case individually. There are infinitely many of them, right? There are infinitely many vectors U. I cannot do it for every single case individually, so I need to do it generally. Okay? So let's take a look at D. First, I'm going to express U in component form. Now, the first thing you should understand about proofs is they are writing. So write complete sentences, capital letter at the beginning, period at the end. Okay? So let vector U equal U1, U2, all the way to UN. I know it is an n-dimensional vector. Notice I'm not saying what the particular values are. I didn't say, oh, maybe this is a 3 and maybe this is a 7. I'm being general. I cannot pick just one vector. I need to prove it generally. All I'm doing is saying, hey, this is an n-dimensional vector, so there are n numbers, n components of that vector. I don't know what they are. They could be anything. Okay, but I know there are n components because this is an n-dimensional vector. Okay? Now for this particular problem, part D here, I want to show there's some other vector. We're calling it negative U here, but there's some other vector so that when I add it to my first vector, I get 0. Okay? In this case, if I can find that other vector and show that there's a vector that when I add it, I get 0, I'm done. Okay? So let's find the vector. Consider -1 times vector U. So I'm scalar multiplying my original vector U by -1. And this is going to give me, using the definition of scalar multiplication, -U1, -U2, all the way to -UN. Okay? Then vector U plus -1 times vector U equals U1, U2, all the way to UN. That's vector U. Plus, and now I'm going to write -1 times vector U. I'll probably drop these parentheses. There we go, that's a little better. So -1 times vector U, -U1, -U2, all the way to -UN. By the way, I just took out those parentheses because I thought it looked a little ugly. If you left them in there, that's fine. It means exactly the same thing. Okay? I just wanted it to look like what I already wrote up here. Now we're going to use the definition of vector addition. For vector addition, I just add corresponding components. So I'm going to have U1 plus -U1 and U2 plus -U2 all the way to my last component, UN plus -UN. Okay? And what I've done now is each one of these components is just numbers being added together. U1 is just a real number. Negative U1 is just a real number. Okay, and I'm just adding them together. I know how numbers are added together. If I take a number and I add its negative, I get 0. Okay, notice I couldn't say that, I can't say that about this, not without proving it. Because these aren't numbers being added together, these are vectors. So I need to show there's something that I can add to the original vector that I get the 0 vector. But with numbers, I know it works. Maybe this is a 2. Maybe that would mean this is a negative 2. I know 2 plus negative 2 is 0. No matter what U1 is, if I add minus U1 to it, I get 0. No matter what U2 is, if I add negative U2 to it, I get 0. And that's going to be true for every component in this vector. And as it turns out, this is the 0 vector. Okay? So what have we done? We've shown that if we take any vector u and we add to it negative 1 times vector u, which is also a vector, I get the 0 vector. I have proven what I needed to prove. I have shown that there is some vector. There exists some vector such that if I take u and add that vector, I get 0. I've even found the vector. So negative u is equal to negative 1 times u. Now, this may seem obvious, and it should. And the reason it feels obvious is because of what we've chosen to represent our vector here. We symbolically represent our inverse vector, our additive inverse, as negative u. And we are used to thinking of a negative in front as negative 1 times. That's not an accident. We chose that because the authors of the textbook knew what the answer to this was. But the idea is there exists some vector, and if we called it something other than u here, maybe we called it v, there exists some vector v so that u plus that mysterious vector v gives me 0. I have found that vector. I have shown that if I take my original vector and just add negative 1 or multiply negative 1 to it and add those two vectors together, I will get the 0 vector. So I've proven my results. And you'll notice in textbooks and such, a lot of times when you end a proof, you write a little box at the end. It feels very good to write that box. Okay? Notice complete sentences. They could be very short sentences. But I start with a capital letter. I end with a period. Even if I have a mathematical expression, I still end with a period. Also, it's best practice not to start a sentence with a mathematical symbol or a mathematical expression. Okay, so notice all my sentences start with words. Makes it a little neater, makes it a little easier to follow. Even this long sentence. And then I have this long sequence of equations that are all equal to each other. But at the end, I still have a period. Okay? So start getting used to trying to write these proofs correctly. Now, with that said, the most important idea from these proofs is the concepts they convey, is that they are logically correct. Okay? Now, for these first set of proofs, they should be pretty easy. But as we move on in the course, you will have to be very careful that all the statements you make are logically true. Okay, let's look at the other proof now. Part E, we want the distributive property over vector addition. So I want to show that if I take some scalar, any scalar k, and multiply it by the sum of any two vectors u and v, then that's the same as taking k times u plus k times v. For something like this, when you want to show that two things are equal, if you can show they're both equal to a third thing, then you are done. Okay, so I'm going to work on each side of this equation individually and show they both are equal to the same thing. Now, when working on proofs, a lot of times you want to go back to the definition. So I'm going to go back to the definition of what vector addition is. I'm going to go back to the definition of what scalar multiplication is. Okay, so the theorem has already introduced vectors u and v, and it's already introduced scalar k. So I don't need to say anything more about that. We know, the reader knows what vectors u and v are, what scalar k is. I'm going to start proof again. But in order to apply the definition of vector addition, the definition of scalar multiplication, I need to break my vectors down into components. So let's let vector u equal u1, u2, all the way to un. And I should say here, this is a different proof. So this vector u isn't the same as this vector u, totally separate. Okay, so when you get to this proof over here, totally ignore what's over here. Not that it's incorrect, but we're on a different problem. Okay, so let u equal u1 to un, and v equal v1 to vn. Okay, now all I'm going to do here is I'm going to apply the definition and calculate the left side of this equation. Then I'm going to apply the definitions of scalar multiplication and vector addition and calculate the right side of this equation. And I will show, once I do that, that they will be the same. Okay? I'm not starting my sentence with a symbol, so I got to find some kind of filler word. So observe. I'll start with the left side of the equation. So that's k times u plus v. Okay? And all I'm going to do is I'm going to swap out my vectors for their component forms and then apply the definitions of vector addition and scalar multiplication. Okay? So I have u1, u2 to un plus v1, v2 to vn. Okay, all I've done is swap out the two vectors for their component forms. Now, because there are parentheses there, the next thing I'm going to do is the vector addition. Okay, so I'm going to let the scalar multiple k hang out here for a while, and I'm going to do the vector addition. I guess I don't need the parentheses anymore because I'll just have the one vector. Add the corresponding components. That's what it means to add two vectors. You just add the corresponding components. Okay? All right, so I've done the vector addition. Next, let's do the scalar multiplication. So I'm going to apply the definition of what it is to do scalar multiplication. So by definition, you just multiply each component in your vector by the scalar multiple. So my first component, u1 plus v1, gets multiplied by k. My second component, u2 plus v2, gets multiplied by k. And so on all the way to the end. Okay, and I'm just going to do one more step. Now, each of these components are just numbers. And so if I'm just multiplying numbers together, not vectors, I could distribute. Okay, I know that for numbers, for real numbers, I have that distributive property. Now, I'm trying to prove it here for vectors and with a scalar multiple. But I know it holds already for just real numbers. And each one of these components is just real numbers. So I can distribute that k. So k times u1 plus k times v1. Second component, same thing, k times u2 plus k times v2, and all the way to the end, k times un plus k times vn. Okay, and I'm going to stop there. That's my left-hand side of my equation, and I've applied the properties about as far as I could take them, right? Now what I want to do is I want to go to the other side of my equation now, ku plus kv, and I want to again apply the definitions of scalar multiplication, of scalar addition, and I want to show that I get the exact same thing. Okay, so next, observe k times vector u plus k times vector v. That's the right-hand side of the equation. And as before, I need to plug in the component forms of my vectors to be able to apply the definitions of scalar multiplication and vector addition. So I get k times my component form of vector u plus k times my component form of vector v. Okay, next we got to apply the order of operations. So according to the order of operations, I do scalar multiplication before vector addition. So I'm going to multiply those k's. So by definition of scalar multiplication, I'm just going to multiply each component of the vector by k. So I get ku1 times ku2 all the way to k times un. Plus, and do the same thing for vector v, kv1, kv2, all the way to kvn. And finally, last operation I can do here is I can do the vector addition. So I'm just going to add the corresponding components of my vectors. So I get k times u1 plus k times v1. First component plus first component. And then second component plus second component, ku2 plus kv2. And keep on going until the last component, kun plus kvn. That's about as far as we can go. Now notice, what we ended up with here and what we ended up with here when we were working with the left side of the equation are the exact same thing. Okay, and I have a string of equal signs here, right? So what that means is this and this are equal. But also, my right-hand side of my original equation and this expression are equal. And since they both equal to this, that means ku plus kv must be equal to k times u plus v. Therefore, ku plus v, and I'll put the middle section here just to make it a little more apparent what we're seeing. They both equal to ku1 plus kv1, ku2 plus kv2, all the way to kun plus kvn. And that's also equal to the right-hand side of the equation, ku plus kv. And that's what we need to show, that this and this are equal. And therefore, we are done.